Well, basic definitions of probability, events, outcome, sample spaces, and the counting principle were part of last night's work. Tonight we're going to add to that. So tonight will be a mix of everything you did for last night's homework plus arrangements, permutations, and combinations. So you might need to use some of the exact same strategies you used on the problems last night. Let's talk about arrangements for a minute. Arrangements are also lineups, and the question is how many different ways could we take a group of items and line them up? And sometimes we need unique lineups, so we have to consider whether we have repeats. Now this is all from integrated algebra. When we worked with arrangements, we used factorials, and just a reminder about what a factorial is and how it works. If I had 4 factorial, that would be the same as, I'll write that a little bit better, 4 factorial. The factorial is just that exclamation point, and that would be the same as writing 4 times 3 times 2 times 1, and your calculator will do those factorials for you. All you need to do is pull up menu, probability, factorial, and we have a little bit and we want the answer to factorial 2, and that doesn't work. What that did is it took the answer from the last one. So what happens is you need to type your number before you actually get that factorial. So if I could do this, I can do 4, and now go to menu, probability, factorial. It'll put the exclamation point after the 4, which is where it needs to be, just like when you write it on paper. When you hit enter, you'll come up with 24. If you look down at the key right next to G, that's a shortcut way of getting the factorial. You'll see it's right next to the question mark. So I could do that as well. I could type a 4. I could hit that key, an arrow to the right, hit the enter. That'll put the factorial there. I'll get a 24. Okay, so I have a couple of questions here on how you might see working with factorials. First way, how many different ways can you arrange the first 6 letters of the alphabet? Well, let me write those first 6 letters of the alphabet: A, B, C, D, E, F. And we want to notice that there are no repeats. We need different or unique ways to line things up. So we have to check, make sure that repeats would give us duplicates in our answers. We don't want duplicates. We have no repeats here, so the answer is simply 6 factorial. And whatever 6 factorial is, you can multiply it out by hand, but there's no need to. Go to 6 factorial, hit the enter key, and the answer is 720. So if you were to sit down and get really busy writing all the different ways you could line up A, B, C, D, E, F, you'd have 720 ways by the time you were finished. Another way to think about that is to think about the counting principle and think about the fact that we're lining up 6 letters. We actually have 6 positions to fill. Here's position 1, here's position 2, position 3, position 4, position 5, position 6, and we're going to put little multiplication dots in between. Well, I have my choice of any of the 6 letters to fill the first position, so I have 6 ways to do that. When I move on to the second position, I've already taken a letter out, and if I've taken a letter out, I have 5 letters left, so I could pick any of the 5 letters for the second position. When I move on, now I have 4 letters left. Moving on again to the 4th position, now there are only 3 letters left to choose from. When you move to the 5th position, there are only 2 letters left to choose from. And when you get to the last position, you have no choice. You only have 1 letter to choose from. So there's only one way to do that. So you can see now that what you end up with using that counting principle and thinking about the 6 separate events or 6 separate choices is you end up with the exact same formula for 6 factorial. Okay, if we have repeats in what we start with, how many different or unique ways can you arrange all the letters of the word Huffington? Well, first of all, I'm going to start with a number of letters in the word: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'd be filling 10 positions. That would be 10 factorial. 10 times 9 times 8 times 7 times 6 times 5, etc. But you may remember from integrated algebra that you have to divide out the repeats. So let's talk about what repeats we have. Well, we're going to have repeats because we have 2 F's. So taking those 2 F's and dividing out 2 F's with 2 factorial. And we also have in this problem, there are 2 N's in this word. There's an N there, there's an N there. So I'd have to divide out another 2 factorial to compensate for the 2 N's. And I don't see anything else that repeats, so we could pick up our calculator and we could type in this fraction the way you see it and that'll do the math properly for you. So you'll get your fraction template. On top, you'll type a 10 factorial. On the bottom of the fraction, we're going to type a 2 factorial. And you'll find the fastest way for yourself to be able to do this. And a 2 factorial, and I didn't put the multiplication sign in there. I don't think that's a problem. Okay, so how many ways can I do that? I've got 907,200 ways. That's a lot of ways. You don't want to do that by hand. Okay, so that's a review of arrangements. You can think of arrangements as factorials, but it may also help to think of them in terms, if you don't have too many of them, it helps to think sometimes in terms of events and using the counting principle, because really that's what it's doing. Okay, part 2. Part 1 of today is arrangements. Part 2 of today is permutations and combinations. So let's see what that's all about. Now, the permutations and the combinations, one of these is a review from freshman year. In freshman year, the only thing you worked with were permutations. And you might remember what the permutations look like. You saw something called NPR, National Public Radio, one of my favorite things to listen to. So National Public NPR, N is the bigger number always. R has to be the smaller number. You can never reverse the order. If one bigger and one smaller number, the bigger numbers always comes first, just like N always comes first in the alphabet. So you put the bigger number first, smaller number second. Okay, when we talk about permutations and combinations, we're going to do this by contrast. Both of them will involve one large group, and that's your N number, and a smaller subgroup, and that's your R number. So we might have talked about permutations involving a group of 10, but we're only going to take 3 things at a time. If that were the case, we would have written 10p3, and we could have gone to our calculator. We did talk about the formula, but we could have gone to our calculator to calculate that answer. You could use the formula by plugging in and doing the separate factorials, but the calculator will let you do it as well. Now, again, if you hit menu and you go to probability, you'll see a permutations option right there. When you see NPR in your calculator, you have to separate it wants to know what the N and the R is. You've got to separate it with a comma. So we'll type 10, comma's down by O there, 3, and hit the enter key, and it'll tell us there are 720 possibilities. Now, in those groups of 3, we were really interested in how those 3 things would line up. We were really interested in the fact that we had a secretary, a vice president, and a president. And we could assign those jobs differently. So we were being very picky about what was going on in those groups of 3. P for picky. Now we're going to talk about combinations. And again, both factorials, both formulas we use factorials, both can be gotten out of the Inspire. So the second formula looks like this. Now let's just look at the contrast here. Permutations for picky. We're being picky about the 3. When we move to combinations, combinations we're being carefree about the 3. So if you saw this written on the paper, 10C3, well, the difference between the two, and it's important to understand the difference. In this group, we were concerned about how these 3 people lined up. We started with a big group of 10. We took 3 of them at a time, and then we were concerned about how those 3 would line up. When we move to combinations, we're still going to take 3 at a time from a big group of 10. But once I have those 3, I'm done with them. I'm just going to say, yep, you 3 are the little group. Now go back and sit down. Then I'm going to go back to my big group of 10, take another group. Okay, you 3 of the group, go back and sit down. We don't really care what's going on once we identify that little subgroup of 3. We don't care what they do, how they line themselves up. We're just putting them out there as a subgroup and then saying, okay, that's it, you're done, your work is over, go back and sit down. Whereas these people in the permutations group, we're going to be working them, we're going to have them lining up in different ways. Again, in the contrast with the formula here, you see that the formulas are pretty close, and we'll talk about this form a little bit later. You'll see these formulas are pretty close with the exception of this number down here. You see, the only difference when we get to combinations is that we're going to divide by something else. And I want you to think about what happens when you start off, when you divide 10 by 2, you get 5. Now we're throwing in an extra multiplier here, so this would be like dividing 10 by 5. And these are just little mathematical examples. They have nothing to do with the permutations or combinations. I'm just trying to show you how these formulas work. If I divide by a bigger number, 5 is a bigger number, I get a smaller answer. So on top with the permutations formula, I'm dividing by a smaller number, I'll get a bigger answer. Down here with the combinations formula, I'm dividing by a bigger number, I'll get a smaller answer. So I'll always have less combinations than I will permutations. Okay, so picky versus carefree, we'll look at a couple of examples of how that works. The students at South High School, a student government consists of 4 seniors, 3 juniors, 3 sophomores, and 2 freshmen. How many committees of 4 students can be formed? Well, this is essentially you deciding between a permutation and a combination. We know we have 4 plus 3 is 7, plus 3 is 10, plus 2 is 12. We have a big group of 12 people. And we know we're going to form a committee of only 4 of those 12. So the idea is this a permutations problem or is this a combinations problem? We have to decide that when we put these 4 students in a room together, do we care how they line up? Is there any information that says that we need to be concerned about who's who in the group of 4? The answer is no. We're not. We are being very carefree about that group of 4 people. So we're going to do this as a combinations problem. So you'll pick up your calculator. You can go to menu, probability, combinations, and we'll type 12 comma 4. And so that means we have a total of 495 committees, 495 different possibilities for forming those committees. It's an impressive number. In the second example down here, we're going to have to work with something we learned last night, the counting principle, and what we're working with today. We have a committee of 4 students, and we were talking about 1 student from each grade. So I'm going to think of this as 4 events. I'm going to choose the first student, I'm going to choose the second student, I'm going to choose the third student, I'm going to choose the 4th student. And I want to end up with a freshman, a sophomore, a junior, and a senior. Well, I'm only choosing if I want 1 freshman, that means I'm choosing 1 out of 2. And I don't care anything about what's going on in those little groups. So out of 2 freshmen, I'll choose 1. And really, there's only one way to line up, and you'll see that with the formulas it wouldn't matter anyway. Let me just finish the problem here. So sophomores, I have 3 sophomores. So out of a group of 3 sophomores, I'm going to choose 1 of them. Out of a group of 3 juniors, I'll be choosing 1 of them. And out of a group of 4 seniors, I'll be choosing 1 of them. Okay, now if you have a 1 down here, remember 1 factorial is just 1. 1 factorial doesn't change anything very much. So when you take a look at that formula, you're doing combinations, your R is a 1. So really, there wouldn't have a whole lot of difference between a permutations and a combinations formula, but you really want to get that idea in your head of choosing the P or the C, the permutations or the combinations, based on whether you're going to be picky about how these line up or whether you're carefree about how these line up. And in reality, when you only have 1, there is only 1 lineup, so it wouldn't matter. At that point, you could pick up your calculator, get those 4 separate numbers if you'd like, and then you could get your answer from there. The big issue with these problems, so these probability problems, is the setups. Really, how do you get to that answer? Once you figure out how to get to the answer, the calculator will do all the arithmetic for you. So it's not about coming up with the right number as much as it is being able to come up with the right strategy to get to that number.